Hello, everyone. Thank you for attending the UALink Consortium's Introducing the UALink 200G 1.0 Specification webinar. Today's webinar will be led by Peter Onufryk, UALink Consortium President at Intel, Nathan Kalyanasundharam, UALink Consortium Technical Task Force Co-Chair at AMD, and Chris Petersen, UALink Consortium Director at Astera Labs. If you have any questions, please feel free to enter them into the Q&A box, and we will address them during the Q&A. With that, I will go ahead and hand it off to Peter to begin the webinar.
Thanks, Nolan. The computing and memory needs of AI continue to grow exponentially. One way to meet this demand is to connect multiple accelerators in a scale-up fashion. While proprietary AI scale-up interconnects exist today, the industry needs an open solution, and that's what UALink is. UALink is an open scale-up interconnect technology that marries the high-speed standard Ethernet SerDes with upper layers optimized from the ground up for AI. UALink scales from 2 to 1024 accelerators, which is ideal for large inference models and small training configurations. For large training systems with many thousands of accelerators, they can be constructed using a mixture of scale up with UALink and scale out using an open interconnect such as Ethernet. UALink is an open industry standard that's governed by a 12-member board of directors from the companies shown at the top of this slide. This board has representation from leading hyperscaler, systems, network and fabric, silicon, and IP providers. One unique thing about this board is that it contains several companies that don't typically participate in industry standards. This highlights the importance of the UALink technology to the broader AI industry. Another thing that highlights the importance of this technology to the industry is that despite being less than a year old, UALink has now over 90 member companies. You can see some of the member company logos at the bottom of this slide. Let's take a look at the UALink timeline. The promoter group that makes up the board companies was announced last May, so a little less than a year ago. In October, we opened up UALink to allow member companies to join. Finally, on April 8th of this year, we publicly released the UALink 200G 1.0 specification. So in less than a year, we developed a specification, and in less than 6 months, we grew to over 90 member companies. Industry specifications are rarely developed this fast, nor do consortiums typically expand so quickly. AI is a rapidly evolving field, and at UALink, our goal is to be agile and deliver open standards that foster the growth of the AI industry. This slide illustrates scale up and scale out. UALink is used within a rack and between a small number of racks. This is a scale up fabric and is shown in blue on this slide. A scale-out fabric, such as Ethernet, is used to build large systems consisting of many of these scale-up racks and is shown in red on this slide. You may be questioning, why not just use a single fabric for everything? The reason is that it is best to have an optimized fabric for each application, and UALink has been optimized from the ground up for high-performance scale-up applications. It uses the same high-performance 200 gig SerDes as Ethernet, which is the fastest standard SerDes in the industry. With 4 lanes per port, this enables a bandwidth of 800 gigabits per second per port. But that's where the similarity with Ethernet stops. The upper layers of the UALink protocol were optimized from the ground up for the small memory transactions needed for scale-up applications. This optimization has led to a simple and efficient protocol which offers low latency, low power, and significant die area savings. So what exactly is in the UALink 1.0 specifications? The UALink 1.0 specification defines an accelerator-to-accelerator interconnect for sharing memory between accelerators. It defines simple memory load, memory store, and atomic operations between these accelerators. And it scales from a small number of accelerators up to 1024 accelerators. Creation of the specification tapped into the experience of the promoter companies in developing and deploying AI accelerators fabrics and systems. Since UALink is an optimized architecture, it enables high performance, low latency, low power, and low die area. Think of it as the same raw speed as the absolute fastest Ethernet with the latency, power, and efficiency of PCIe switches. However, what makes UALink great is that it's open. This enables interoperable products in the market and harnesses the innovation of over 90 member companies to drive leading-edge capabilities into the specification. Finally, UALink uses the ubiquitous Ethernet infrastructure. This includes things such as cables, connectors, retimers, and management software. So with this brief introduction to UALink, let me turn it over to Nathan to dive into the technical details.
Thank you, Peter. Next slide, please. Good morning, good afternoon, and good evening to everyone online. So Peter provided an overview of scale-up pods, UALink specification goals, and benefits. In this section, let us start with an overview of the UALink stack. And as you can see, the link stack is comprised of a physical layer, a data link layer, transaction layer, and protocol layers. And also, as Peter noted, one of the critical goals of UALink is to leverage Ethernet infrastructure like cables, retimers, connectors, and management software. So UALink starts with a standard Ethernet physical layer. This is important. UALink supports 1, 2, and 4 serial lanes running at a serial rate of 212.5 gigabits per second. Optionally, UALink also supports a lower data rate of 106.25 gigabits per second. So a UALink port supports max data rates of 200 gig, 400 gig, and 800 gig gigabits per second with 1, 2, and 4 lanes. A bifurcatable 4-lane config is defined to be a station, and a station may have 1, 2, or 4 ports. The physical layer also uses a standard Ethernet FEC, and in addition supports low latency options through 1- and 2-way code interleave. A few minor modifications to the physical layer is needed to fit the 640-byte DL flit into a 680-byte FEC code word. Now, if you shift your focus from the PL to the layers above, the data link layer, transaction layer, and protocol, they are all unique to UALink. Now, later on in the deck, we'll cover the reasons to create a unique stack for the upper layers. Another important goal is to create an efficient and yet simple direct load store protocol for scale-up communication between accelerators. In order to accomplish that, UALink uses fixed payload for each of these layers. So the TL flit is 64 bytes in length, DL flit is 640 bytes in length, and the physical layer is 680 bytes. Now, in order to provide applications flexibility, UALink 1.0 is provisioned to support up to 4 virtual channels. Protocol also supports multiple address spaces, which may be used to identify host physical address, network physical address, or MMIO. And these are all implementation specific to allow implementations to innovate on their own. UALink also supports a link level retry and credit-based flow control. Protocol is designed to facilitate low latency operations with the total round trip latency target less than a microsecond. And in order to support low latency and high efficiency, UALink allows packing requests and responses into the same frame or a flit. Specification also allows packets to many targets to be packed together in the same frame. And we'll review these examples a little bit later. Finally, UALink optionally enables implementation to build full confidential compute solutions with end-to-end encryption and authentication. Next slide, please. Okay, so let us review each of these layers, starting with the protocol interface. UALink protocol presents a very simple interface to the accelerator and the switch cores. AI workloads demand symmetric communication between accelerators. Accelerators and switches both are expected to enable simple symmetric protocol. The protocol interface, as you can see, has a request command, request data, write response, and read response channels. The read response channel also includes additional data. Since it's a symmetric interface, there are two copies of the interface labeled originator and a completer. Originator interface is an initiator of requests. Now, when implemented on an accelerator, this interface is used in the outbound direction to send requests to other accelerators, and responses returned from the remote accelerator is processed through the same interface. Now, the complete interface is a responder interface. Now, when implemented on an accelerator, this interface is used in the inbound direction. Requests from the remote accelerators targeting local memory is processed through this interface. Their responses returned from the local accelerator are processed through the same complete interface and sent back to the accelerator which initiated the request. UALink identifies all accelerators in the scale-up domain through a unique physical identifier. Requests and responses are tagged with the source and the destination identifier. Switches route these packets only based on ID and does not use any other field. UALink protocol is also provisioned to support multiple address spaces, as we looked in the previous slide. The protocol defines a 57-bit address field and is left to the implementation on how it gets used. Now, this gives accelerators maximum flexibility and the ability to innovate as well as meet unique requirements per accelerator. This also means that the UALink 1.0 only enables communication across homogeneous set of accelerators. And since switches are ID routed, switches can be used by any accelerator which supports the UALink protocol. Finally, UALink is mostly a source-ordered protocol. Completions for all requests, reads, writes, and atomics are unordered. Only requests to the same address from a source to a destination are ordered through the switches. The exception is when encryption and authentication is enabled. UALink protocol uses AES 256 GCM, hence encryption is organized as three independent streams: a request stream, a read response stream, and a write response stream. Packets within a stream must stay ordered from a source to a destination. Next slide, please. Now, next layer in the stack is the transaction. The transaction layer converts protocol messages into flits. Transaction layer uses a 64-byte flit format. It is organized in 4-byte sectors, and there are 16 sectors within a 64-byte flit. TL is also divided into an upper and a lower 32-byte half flit. Each half flit can carry control or information or data. Control half flit is used to carry control info or headers for requests, read responses, write responses, flow control, and if there is nothing to send, no ops. Control can only be placed in the lower half flit. Data is allowed to use both the half flits, upper and lower. It is used to carry read response data, write data and associated byte mask, as well as atomic operand data and the associated byte mask. Further to note is that only partial writes and atomics carry byte mask. They're identified, the full writes are identified through special commands called write full, and they don't need to carry the byte mask. Requests and responses may also be compressed. An uncompressed request is 16 bytes or 4 sectors. A compressed request only requires 8 bytes or 2 sectors. And the compression is achieved through an address cache implemented in the TL. A compressed response is 8 bytes, and an uncompressed response is 8 bytes, and a compressed response is only 4 bytes. Since write responses are very small packets, it is highly inefficient to pack them into independent frames, let alone per destination. So TL uses a highly efficient packing style at line rate as they arrive from the protocol interface. So the two examples shown on this page are the rightmost one is the most efficient packing efficiency shown. That's 95.2% protocol efficiency using both compressed requests and responses. This packing utilizes 3 requests and 2 responses in the first control word. It is followed by the 768 bytes of data associated with the 3 requests, each 256 bytes each. In the second control word, we carry 2 requests and 3 responses and a flow control packet. That is followed by a 512 bytes of data. That is what achieves the 95.2% protocol efficiency. Now, the second example uses uncompressed requests and compressed responses. It is not always possible to compress requests. Responses can always be compressed. And in this example, the effective protocol efficiency is 92.3%. So as you can see, the UALink is designed to provide very high link efficiency with load store small packets, which are used for accessing local memory, remote memory, or the host memory. So the same request and memory ordering model can be followed for all 3. Next slide, please. So the next layer in the stack is the data link layer. It sits in between transaction and the physical layers. Data link layer packs 64 byte TL flits into a 640 byte DL flit. Each DL flit also carries a flit header, 5 segment headers, and a 4 byte CRC. These together have 12 bytes of overhead, so the efficiency of the DL layer is around 98%. As noted earlier, the physical layer covers FEC and additional encoding and uses 40 bytes for carrying that FEC and additional encoding. However, the RS-544-514 standard FEC overhead, that is handled through a higher signaling rate, and UALink, similar to Ethernet, uses 212.5 gigabits per second. DL also provides a reliable transport through link level retry support. In addition to that, there's port level reset, station level reset, and a few other RAS features which is supported through the DL. DL also provides UART style messaging service between link partners. UART messages may be used for in-band queries, key exchanges, and other services via firmware. Next slide, please. So now that we have gone through the UALink stack, let us look at how it is used in the system. Peter covered a scale-up pod example. This is just digging into a little bit more detail. So the primary use of the UALink specification is to create a scale-up pod of a group of accelerators. The maximum number of accelerators supported in these systems is 1024. In order to keep the standard simple and to allow easy extensions to create in-network collectives and future expansion, UALink 1.0 is limited to a single tier of switches. A few things to highlight in the example shown. Bandwidth per accelerator is fully scalable, right? And it is managed by adding more switch planes. So in this example, N accelerator ports require N switch planes, and N could be any number. The number of accelerators within a pod is controlled by the lanes or ports supported by the switch. In this example, each switch plane supports M ports, each with 2 lanes to connect to M accelerators. A pod may also be configured as many virtual pods. The vPods are completely independent. Reconfiguration of the virtual pods do not or must not impact other virtual pods in the system. Similarly, error in one vPod should not impact others. Error recovery is also expected to be contained to a vPod through port and station resets. There are some class of errors, like internal switch errors, which may impact an entire switch plane and likely the entire pod. These class of errors will require an application restart. Next slide, please. This is the last slide of the quick technical overview. The data flow discussion is to review why UALink stack above the physical layer is unique to UALink. Accelerators for both training and inference use multiple stacks of high bandwidth memory. And as these model sizes grow, compute, memory bandwidth, memory capacity, and interconnect bandwidth all tend to grow proportionally. In order to utilize the HBM bandwidth efficiently, or accelerators typically interleave finely across memory channels at 256 byte boundary or 512 byte boundary. This allows to maximize local memory efficiency of the, when accessing local memory, pure GPU memory, and the host memory. In addition, load store memory model use small packets. Many of the instruction set typically support 32 byte or 64 byte as the largest load store instruction. Another issue is the concurrent communication amongst the set of GPUs within a group. In a load store network supporting end-to-end frames with an Ethernet-like packet network, at a minimum adds latency. To efficiently pack these small packets also requires supporting variable frames, as well as accumulating requests and responses per destination. These add significant area to the accelerators. UALink TL instead packs requests and responses as they arrive from the protocol interface. Since requests and responses are independently flow controlled between the TLs and between the protocol layer blocks, requests and responses can be packed together. Also, allowing packets to multiple destinations to be packed together, it saves significant amount of area and latency. Finally, TL is a very lightweight implementation. It is both low latency and efficient in its area. Now, implementations may differ, but a rough expectation is around 0.3 square millimeter per UALink stack in N3 technology. Also, area is dependent on the round trip latency tolerance, which includes cable length, and retimers in the path. But as you can see, it is designed for efficient implementations. Next slide, please. All right, that concludes the technical overview. Chris Petersen from Astera Labs, who's also UALink Consortium Board Director, will cover the system level specifications.
Thank you, Nathan. So as we developed this spec, it was important for the consortium to make sure that we considered not just the interconnect itself, as well as the silicon implementations, but also understand and develop the spec around how the silicon gets used, how it gets deployed, and how it gets integrated into systems. These days, when we think of systems, it's not just a small server within a rack, but is scaling to the rack itself, as well as across multiple racks, depending on the size of the cluster that you're trying to build. So as we worked on this, we wanted to ensure that we provided the right mechanisms to be able to manage and control all of the components within this particular pod. So when we approach this, we look at this in essentially three different categories. So if we start at the diagram on the right side, let's start at the bottom here. And within these racks, there are system nodes. This is very similar to a traditional AI server system. It has typically CPUs in it, the accelerators themselves, and then the supporting components for both the accelerators and the CPUs. So this is what we refer to as a UALink system node. In this diagram, we're showing 3 of those. And in this example, we're showing 4 accelerators per system node. The other critical component here is the UALink switch platform itself, or ULS, as we often describe it. And this has essentially a platform that has 1 or more UALink switches on it, plus the local management solution, which may or may not be some form of CPU subsystem. And then finally, we need some orchestration mechanism, some orchestration layer that needs to be able to handle the UALink pod configuration, all of the management aspects, and all of the control plane aspects. And that's shown at the top here and is referred to as a UALink pod controller. When we started working on the management solution here, it was important that we provide mechanisms in such a way that we can support a variety of different management approaches and management models. There's quite a variety of implementations out in the industry at this point, and so it's important to be able to provide the common mechanisms for it, but not necessarily provide a detailed implementation for every possible management model or approach. As a result of that, we're looking at this from the perspective of if you'd like a more Ethernet-like appliance type of model, that can be possible. Or if you would like a more lightweight PCIe switch-like model, that is also possible. The way the consortium is defining the management mechanisms here is through a common set of workflows and APIs that need to be defined. So as an example, as you bring up a pod, you need to be able to go in and configure what accelerators and what switch ports are part of a particular virtual pod. So the pod controller provides the overall orchestration for this and provides the accelerators and the switches with the relevant IDs and information to be able to create that configuration. Finally, as we are working through defining these mechanisms, we don't want to reinvent things. We'd like to leverage as much from other industry specifications as possible. So when relevant, we try and reference to OCP specs, things like CPER or other telemetry and accelerator management or RAS specifications that are already out in the industry. And instead, we focus specifically on the UALink related capabilities that we needed to define. Let's take a little bit of a deeper look at this. So the example here shows each of the 3 components I just described. So the UALink system node is shown in green here on the left. And as I mentioned, that contains the CPU in red here, the blue accelerators, and then some form of management subsystem. So in a traditional server, that is often a BMC or a baseboard management controller. On the right side is the UALink switch platform with the blue UALink switches on it. And then at the top is the pod or rack management controllers. Within the UALink system node, we need to have a mechanism to be able to set up and monitor and control the accelerators themselves. So we're defining a set of interfaces and APIs that could access the accelerators either out of band or potentially in band, depending on what your management preference is. And those APIs will help configure the accelerator to be able to join the UALink pod, as well as collect telemetry to get a sense for what the health and reliability of the current pod is at this point in time. On the right side in the black box is the UALink switch appliance. So for the control and management aspects here, this diagram shows two separate CPUs providing the management and control aspects, but those could of course also be a single common implementation. Essentially what we're defining here is a UALink switch management agent. This agent will talk to the UALink switch and provides the switch configuration, the telemetry, and any of the other setup needed or reconfiguration needed as things evolve and they're deployed in the field. Finally, there's the device management and platform management aspect of things that also needs to be considered. And this is things like collecting temperature information, power information, voltage information, and so on. And that provides the telemetry up to the upper layers. So the pod controller here at the top in the purple box is ultimately responsible for configuring the entire pod, which may span one or more racks. This is the entity that has the visibility to understand what devices are in which particular racks, the specific accelerators, the specific switches, and also provides the orchestration for all of this. So as an example, to create a vPod, the pod controller will need to understand which particular accelerators and which switches and which switch ports need to be as a part of that particular virtual pod. And it will then send that configuration information down through the agents in the system node and the switch appliance and push that down into the silicon to configure those and allow you to partition the pod. All right, so we talked a little bit about the switch management and some of the system aspects, but now let's take a look into where we're going next with the consortium. So the next piece that the group is working on is to provide an alternate physical layer implementation. So today we've been focused on Ethernet, but there are some applications that would like to build the UALink stack on top of a PCIe physical layer. The way the specification has been developed, it allows us to leverage the exact same common protocol, transaction layer, and security mechanisms at the higher level of the stack. And it allows us to swap out the data link layer and the physical layer to whichever makes sense for the particular application. So the specification that we're currently working on and is expected to be released in July of this year is really focused on enabling the PCIe Gen 7 or 128 gigabits per second per lane implementation as an alternative to the Ethernet implementation for some applications. The next big milestone for the consortium will be to implement an in-network collective mechanism and specification for that. The timeline for this is targeted toward the end of this year and is expected to provide all of the capabilities, control plane management, to allow us to implement in-network collectives within UALink switches in the future. The final area that is under discussion as a part of the UALink consortium is to consider implementing a chiplet specification, which would allow you to implement the UALink capabilities, whether it's the physical layer or the physical layer plus the rest of the stack, into a chiplet of some kind, and should facilitate simpler and broader deployment of the UALink solution. All right, now that we've talked through everything that the UALink spec supplies and provides, I wanted to take a moment just to wrap up. Ultimately, UALink is an open, standardized scale-up fabric solution that's really built around load store mechanisms and very small packets, and packing those efficiently to allow AI accelerators to effectively and efficiently communicate with each other. Ultimately, what this translates into is it allows us to continue to keep pace with the rapid evolution of AI models, especially as we get into agentic AI and reasoning AI, and we get into ever more complex inference, for example, that becomes more reasoning based and allows us to keep up with that rapid growth. What I want to leave you with here is that overall UALink has been purpose-built specifically for scale-up solutions and provides an efficient, low latency, and high bandwidth interconnect solution for that type of for this application. The UALink implementation is efficient because it's really been focused on implementing only the capabilities required for this scale-up solution. That translates directly into lower die area, both on the accelerator side as well as on the switch side, and the resulting power efficiency you get from that. It's also focused on low latency. In this particular case, really all of it has been architected to be able to get through the various layers of the stack as efficiently as possible. And because it is ID routed, it also allows the switch implementation to be very straightforward and simple. It allows us to implement a non-blocking crossbar, and the packets can do a very simple lookup on the switch side, which prevents any need for very large buffering, and there's no challenges with head-of-line blocking. Again, ultimately resulting in low latency and consistent low latency. Finally, with the efficient packing mechanisms that we've implemented, we're able to maximize the available bandwidth for the links and allows us to use that bandwidth as effectively as possible, thereby maximizing the performance of the training or inference workloads. At the end of the day, the net results you're going to see from this is that the training runs will be able to complete faster, your inference workloads will be more efficient, your time to first token will reduce, and your tokens per second will continue to improve. Thank you for joining us today. I would strongly encourage everyone who is not yet a member of the UALink Consortium to please consider joining the consortium and helping us to continue to develop this specification going forward. If you'd like to learn more about the specification itself, it is available for download on the UALink Consortium website. Thank you everyone for your time today.
Excellent. Thank you, Chris. Now we'll go ahead and dive into the Q&A. If you have any questions, please feel free to submit them into the Q&A box. So our first question for today is, when do we expect products to become available in the market?
I can take this one, Nolan. So UALink is a industry standard setting consortium. We can't really speak to any particular company's products or timelines. However, what I can say is typically when you develop a new technology in a new consortium, it takes about 18 to 24 months to see products. We expect with the pace of AI to see products with UALink much sooner than that.
Excellent. Thank you, Peter. The next question is, how is UALink different from PCI Express technology?
So I could comment on this one, Nolan. So the first critical difference to notice is that UALink is specifically built for scale up. And it is also built in such a way that it allows flexibility on the physical layer. And in this particular case, since we've been talking a lot about the Ethernet physical layer, the first notable difference here, of course, is that Ethernet 200 gig is widely available at this point. And so you get a significant increase in bandwidth as a side effect of being able to run on top of that Ethernet physical layer. The second piece here is that while there are some similarities, certainly to PCIe from a memory semantic perspective, the big benefit here is that UALink is really focused on a much simpler overall mechanism here and doesn't have a lot of the optional features and capabilities that PCIe does. That, at the end of the day, allows for more efficient implementations and improves both area and power efficiency.
Great. Thank you, Chris. Our next question is, how much industry demand are you anticipating for UALink technology? Do you see UEC and UALink being the way forward for accelerators?
I can take that one, Nolan. So we've grown from essentially just a promoter group to over 90 companies in approximately 6 months. So the growth has been fantastic. We have IP providers, system companies, hyperscalers, all actively engaged in UALink. So we see a lot of demand and interest in UALink, and we think it'll be extremely successful. I think the question on UALink and UEC, how do they work together or not? We view UALink and UEC as complementary technologies. UALink was architected from the ground up to be very efficient, low latency, optimized for scale-up fabrics, and UEC is perfect for scale-out fabrics. So we view the two as complementary.
Excellent. Thank you. The next question is, when you say low latency, what is the lowest latency possible? For example, could it be used to access DRAM memory directly, replacing the standard parallel DRAM interface?
Yeah, I can take this question, Nolan. So it certainly is not a replacement for direct memory access, right? The latency target, as I mentioned, is end-to-end load to use is about a microsecond, because requests to the peer accelerators have to go across the accelerator to the switches and to the remote accelerator and back. So while we are designed for low latency, the latency within the accelerator itself is a significant component. What we are trying to reduce is the latency through the switches, and hence it's not a replacement for a direct load store or a direct memory attached interface.
Excellent. Thank you, Nathan. Our next question is UALink cache coherent?
I can take this one. No. So UALink is I/O coherent. It is not cache coherent. It is software coherent, and it has only simple load stores and atomic. There are no snoops which go across the UALink.
Excellent. Thank you. So our next question is, when is UALink going to have 400 gig PHY?
I can take a look at that, right? So I think the industry is trying to figure out where 400 gig lands. We are anticipating something around the end of next year for UALink.
Excellent. Thank you, Peter. This question is directed to Chris. How is dynamic reconfiguration of vPods handled?
So in a scale-up network, it's important to remember that all of the accelerators are working together within a vPod on a single job. So that's important because if a reconfiguration is required, for example, because a link goes down or an accelerator fails, that essentially causes the job to stop. As a side effect of that, the pod controller will need to be aware of that particular failure and what component has failed. It will then need to take that into account to map around that particular failure with the remaining components that you'd like to continue to include in the vPod, and then reissue configuration information to those updated components.
Excellent. Thank you, Chris. This next question is directed to Nathan. Is there a detailed protocol format available?
So the specification does have detailed protocol formats for all the layers, right? The protocol layer is called the UALink protocol layer interface, UPLI. And then the transaction and the DL is all specified in great detail in the 1.0 spec. So if once people look at the specification and if there are further questions, we can certainly answer them offline.
Excellent. Thank you, Nathan. Our next question, does UALink support optical?
Do you want? So I can take that question. So in the standard, we do not get into the optical detail. That doesn't mean that UALink cannot be used with our optical interfaces. The primary focus is electrical and especially 200 gig IEEE 802.3DJ.
Great. Thank you, Nathan. Our next question, is the UALink LLR the same as the UEC LLR?
I can take that question. We do not have an MOU with the UEC. So generally, we haven't tried to reconcile the two LLRs. However, since UALink stack is, as I noted earlier, is purpose built for scale up pods, it is likely expected to be different.
Great. Thank you, Nathan. Our next question, how will UALink compare to NVLink in terms of bandwidth and latency?
We don't have a detailed comparison available. However, we think they're very similar. I think what distinguishes UALink from NVLink is that it's open.
Thank you, Peter. Our next question, how does UALink compare to or differ from CXL?
So I could take a stab at this one. So I think the key here is, as Nathan already mentioned earlier, UALink is not cache coherent, whereas on the other hand, CXL is cache coherent. So that is one significant difference. They are certainly both memory semantic, but I think the other key difference here is that CXL is built on top of the PCIe stack and physical layer. Whereas UALink has the flexibility to also run on top of the Ethernet physical layer, which certainly provides an increase in the per lane bandwidth.
Thank you, Chris. Looks like our next question, are we expecting the UALink protocol layer to interoperate with UCIe?
I could take this one. So we're exploring standardizing a chiplet interface, and UCIe is a great die-to-die technology, but that's still open. What will happen there?
Thank you, Peter. Our next question, Are there RDMA operations supported in UALink?
Yeah, I can take this one. Certainly, it is supported. Internally, within the accelerators, there are many DMA engines, and it's not as you imagine an Ethernet Rocky DMA would look like, but internal accelerator DMA engines can do the copies. So the short answer is yes, RDMA, or DMA transfers are supported.
Perfect. Thank you, Nathan. Our next question, can the UALink switch be embedded in a single server like a PCIe switch?
Sure, I can take this one. So the UALink spec allows a variety of possible implementations. It is entirely possible for someone to either build UALink switches in switch platforms at the rack level, as I described earlier. It is also possible if you have a sufficiently small radix or you want to build a sufficiently large platform to be able to put a UALink switch within the platform itself. So there's nothing within the spec that prevents you from doing so.
Great. Thank you, Chris. I think maybe we have time for one more question here. So the last question, are there currently any plans for interoperability testing for solutions from different providers?
I can briefly cover that one. So we have created a compliance work group that's working on a compliance program. We're not ready to talk about that yet, so stay tuned.
Excellent. Thank you, Peter. So that was the last question that we have time for today. We received a great number of questions, so we'll plan to cover answers to those questions in a recap blog following the webinar. So stay tuned for that on our website. The webinar recording will be made available on the UALink Consortium YouTube channel, and we will also be making these slides available to download on our website. So thank you everyone for attending the webinar.
Thank you.
Thank you, everyone.
Thank you.